My next quick tip for the final exam involves thermal circuits. The thermal circuit analysis is pretty straightforward. I'm not going to say too much more about this that I haven't already said in the lecture videos, but probably the most common mistake that I see students making is in setting up the correct signs on the equation, what's positive and negative. Now, the thermal circuit analysis, as we mentioned, doesn't really follow the sign convention that we've been talking about in class. It's sort of a different type of analysis, a different perspective. When I give you a problem where you'll have to perform a thermal circuit analysis with conduction and convection, you're going to know what direction heat transfer goes. It's going to be obvious from the problem. So this particular problem here, you can see that the temperature 1 is the highest temperature 2 is a little bit lower, 3 is lower, and that T infinity is the lowest temperature still. So what direction is heat transfer going in this problem? Left to right. Going in this direction, okay? So since I know my heat transfer is traveling in this direction, then I can set up all of my proper thermal circuit equations based on that orientation. So for example, I would have three thermal circuits, or three resistors, thermal resistors here, one for conduction, a second for conduction through slab 2, and then finally I would have a thermal resistance for convection. So I've got conduction, let's call that R conduction 1 and R conduction 2. And then this will be R convection, okay? So I can write a very simple expression, a very simple resistance expression for each device individually. If I consider my temperatures to be located at these nodes, that's my T1, T2, T3, and T infinity. So let's write an equation for the very first resistor. So since I know heat is traveling from left to right, I know that T1 is my bigger temperature. I know that T2 is my smaller temperature. So when I write my delta T is equal to Q dot times R, again, this is the analogy, the delta V is equal to IR. That delta T, I'm always going to write it as a positive quantity. T1 minus T2 is equal to Q dot times the R conduction 1. If I were to do the same thing for the middle resistor, I would have T2 minus T3 is equal to Q dot times R conduction 2. And that final resistant, or the final resistor equation there is going to be T3 minus T infinity is equal to Q dot times R convection. So this is something that to be really clear about, you always want these equations to be positive. You'll never get like a negative Q dot or a left-hand side that ends up being negative if you set all your equations up properly. And so usually solving a thermal circuit problem is a matter of setting up these equations properly and just solving that system of 3 equations and 3 unknowns, or 2 equations and 2 unknowns, however it ends up. And if you get that, if you had a T2 minus a T1 instead of a T1 minus a T2, if you switch that order, you're going to come out with incorrect mathematics, and you're going to lose a few points. Most important thing is you get the equations set up. Now, obviously, let me say one more thing about this, and as part of the thermal circuit analysis, the cool part about this is that we can combine all of these 3 individual resistors together to form one equivalent resistor. So this equivalent resistance would have an equation that looks like T1 minus T infinity, again, bigger temperature minus smaller temperature always, is equal to Q dot times R equivalent. And again, I'm basically replacing all 3 of those circuits with one total circuit. There's my T1, there's my T infinity, both sides of the system, and my R equivalent is just the series sum R conduction 1 plus R conduction 2 plus R convection. The odds of seeing a thermal circuit problem on the exam are really high. All right, everybody, good luck.